Okay, so the very last concept in section 1 of chapter 2, quick little thing, is just thinking about the different ways in which we can represent functions, and there's 4 general ways we could do that. So when we want to represent a function, express what a function is, a relationship between input and output variables, we can do that verbally through a sentence, right? Double the input plus 5, or the square root of the input minus 4, those kinds of verbal descriptions. We can do it algebraically, the most popular way of doing it, some sort of an equation, 3x plus 5 or something. Visually with a graph, right? So a graph is a representation of a set of ordered pairs, typically an infinite set of ordered pairs. And we're looking for a pattern that's sort of established by the graph. And there's some classic graphs, some typical graphs that we work with quite a bit. Or numerically with some sort of a table, either a very finite number of values. Either the function is only defined for a finite number of values, or the table provides pattern that we can use to find other values, right? If we can see from a table that we're always doubling the input, we can see that the pattern exists and use it. So see, a single function can be represented in 4 ways. Okay, so some examples. So verbally, right? So here's an example verbally. To convert the Celsius to Fahrenheit, multiply the Celsius temperature by 9/5 and then add 32. Right? So it's a verbal description of the relationship between Celsius and Fahrenheit. Okay. Algebraic formulas, right? So here's a classic formula for the area of a circle. So written in function notation, a of r equals to pi r squared. So pi r squared is a very famous algebraic expression. We can also describe things graphically. So here looks like it's a seismograph for earthquakes, right? So we can see visually what was happening at various time points. And in some cases, each one of these representations of a function has its own benefits, and in some cases the graphical method is clearly the only way to really represent information, or the best way to represent information. Okay, and then with a table. So here is a table of values. Looks like this is weight, 0 to 1 in ounces, 1 to 2 in ounces, and then dollars. So this is the cost of mailing a first-class envelope. So 98 cents as long as it weighs less than or equal to 1 ounce. If it's greater than 1 but less than or equal to 2, $1.19, and so on and so forth. Good. So here's another representation of a relationship between 2 variables. Any questions? Fairly easy, right? This chapter is going to be really easy. We're going to fly through the first few sections, I think. Good. Okay, so practicing. Let's practice with the relationship between Fahrenheit and Celsius. So we had the verbal description. We saw over here that the verbal description was to convert a Celsius from Fahrenheit, multiply the Celsius temperature by 9/5, then add 32. Okay, so we want to describe that in 4 ways. So algebraically, numerically, using a table of values, and then visually using a graph. So if we have Fahrenheit described as F of C, where C is the Celsius value, well, we're supposed to multiply the input value by 9/5 Celsius, and then add 32. To convert from Celsius to Fahrenheit, so starting at Celsius and leading to Fahrenheit, multiply the Celsius by 9/5. Okay, good. So we have a algebraic formula, right? Easy. Numerically using a table of values. Okay, so again, we can just sort of establish a table like this where we have an input value of C and an output value of f of C. And then we can just choose different results here. Why don't we start off with a super easy one? Why not 0? 0 is always good. And let's put these values here. 9/5 plus 32 means we only get 32 there. Let's pick another one. How about another convenient one would be something that's a multiple of 5, right? I could choose 1 or 2 or 3, but then I would end up with a fraction here, and then I'd have to add 32 plus a fraction, common denominator, right? So it's a lot of work. Why not choose something convenient that will result in something I can easily do? So if I let C equal to 5, let's put 5 over here. Then I end up with 9/5 times 5 plus 32. So that's going to cancel out to give me 9. 9 plus 32 gives me 41. Okay, and you get the point. So we just keep going. We can come up with a table. Good. And then visually, using the graph. Okay, so we just graph this guy here. We can tell it's a linear equation where the slope is equal to 9/5, and 32 indicates for us what the y-intercept is going to be. So f of C equals to 9/5 C plus 32 means that this part is the slope, and from here, not the 32 is the y-intercept, but 0, 32 is the y-intercept. Right, and that's because this is linear. So if we wanted to do like a rough sketch of this, we know we could do it in the following way. It doesn't have to be a perfect graph and doing it by hand. You just have to kind of identify some of the key things, that's all. So here is a rectangular grid. We know that the m, the slope, is going to be equal to 9/5. And we know that the y-intercept was 0, 32. Okay, so we have a point here, 0, 32. You just put it there and label it. 0, 32. And then I can use the slope, having a value of 9/5, to use this as my rise, and this guy as my run. Remember, slope is rise over run. So I can create a little triangle here where I know this is going to go 5 units this way, and I know this is going to go 9 units this way. And it's not really up to scale because according to my graph, the distance from here to here is 32 units, but then this distance is 9 units. So it's not quite up to scale, but that's okay. As long as we label ordered pairs, then people will be able to follow what's going on. Okay, so we should arrive at another point on the line, and then we can connect them. Good. And so let's label it. If you're going to do this, it's important to label points because it's not really up to scale, and I'm just kind of sketching it. So you need to label your points. Okay, so we started at x equals to 0, and we traveled 5 units this way. So I know that this ordered pair is going to be start off with a 5, and then from in the vertical direction, we started out with a height of 32, and we went up an additional 9 units, so we get the 5, 41. And so there you go. We have two ordered pairs. We have a line. We're pretty good. Maybe label the actual line. Maybe label the axes. So this is a case where this is the C value for Celsius, and then out here is the F. Right? So the C axis, instead of X axes, we can use the C axis, the F axis. And then this equation right here is F of C equals to 9/5 X plus 32. Any questions? Okay, so this is what the author did as well. Wrote down the equation in this format, same as what we did. A little table of values. They chose different ones. I chose 0, 5, right? Looks like the author went by multiples of 10. That's fine. Another good choice, since 5 goes into 10, and we get some easy evaluations there, right? Like for example, for example, for this one, we would have F of 20 is equal to 9/5 times 20 plus 32. 5 goes into 20 4 times. You get 4 times 9 gives you 36 plus 32, which gives you 68. And that's how they got the 68. And then the graph. Good. So they didn't label the ordered pairs, but they labeled the vertical and horizontal axes. Hopefully good enough to be able to tell that 10 traces to 50, right? So that's the drawback of graphs, that they don't give you very precise answers, right? If you're just looking at this graph, if nothing else was given to you, it's kind of hard to tell 20 leads to, you know, somewhere over there, and it's kind of hard to tell exactly where it is. So graphs, you lose precision when you use a graph, but you gain perspective, right? Sort of a global perspective of the pattern that happens at large. So there's a lot of value to graphs. Any questions? No? None? Good? Good. Okay, that was the end of section 1 in chapter 2. Hopefully pretty easy stuff. Moving on to point 2. Okay, another really easy section. Okay, so in this section we're going to be looking at functions by plotting points, graphing piecewise defined functions, vertical line tests, and then which equations represent functions. All easy things, I think. Okay, the most important way to visualize a function is through its graph. Like I said, there's a lot of value to being able to look at the graph of a function. We get to see the relationship between the input and output variables in an easy way. It's an easy way to interpret that relationship. And one of the first ways that we learn to graph anything is just by plotting points, right? So we find ordered paired solutions to the equation that's provided, or the relationships that's provided, typically through an equation. And if it's not an equation, you probably want to take the first step is to write it in the form of an equation if possible, and then graph those ordered pairs, and from there hopefully a pattern, a useful pattern might emerge. Okay. So a function f of the form f of x equals to mx plus b is a linear function, as we've been working with already, because it's the graph of its because the graph of the equation y equals mx plus b, which represents a line with slope m and y-intercept. This author keeps doing this. It's not y-intercept b, it's y-intercept 0, comma b. Y-intercept 0, comma b. And then we have a special case, linear code occurs with m equals to 0. Okay, so let's look at those, right? So this is all linear equations of the form y equals mx plus b. Y equals mx plus b. And now with our newfound function notation, it's f of x equals mx plus b. Right? And that's where this guy represents the slope, the angle of the line, and this value here, 0, comma b, and represents the y-intercept. So let's look at that family of functions. So let's look at Desmos again. So again, for those of you who didn't see yesterday's class, it's Desmos, DESMOS.com, and then you choose calculator, and you get to this. So linear equation. So y equals to, say, 3x plus 2 is a linear equation where the slope is 3, right? So this the steepness of this line is identified by this 3, and 0, comma 2 is the y-intercept here. And as we change the slope, so that the slope changes from 3 to 8, it gets steeper. If the slope changes to something like a really small decimal, like 0.01, then it gets less steep. At 0, it becomes a horizontal line. And then if we have a negative value, like -1, then the angle goes down this way. Remember, think of it as like a little stick person walking from left to right, going downhill, therefore the slope is negative. We can create with this guy a variable, or actually let's go with m, like this. And now this little value m, the slope, is evaluated by this little slider here. So you can see that as I move this and I make m larger and larger and larger, like right here it's 3, and then larger and larger and larger, like here it is 5. So as we go in this direction, the steepness climbs that way, and then we go all the way back down to 0, and then it's horizontal. And then as we go this way, it becomes steep in the other direction, right? A very big, right? It keeps going. And then the other variable here is the b. The b determines the y-intercept, which is this guy right here. And let's label it as a point. 0, comma b. Label it, right? And then, so that's the y-intercept, 0, comma 1. And as I slide this up or down, it changes where it crosses the y-axis. So with a combination of these two things, we're able to graph almost everything. The only thing we can't graph this way, the only thing that's not really defined by all of this, is vertical lines, right? Vertical lines are a unique case. So even though the slope can get really big in the positive direction, right? A very big positive steep value here. Let's go with let's say we have y equals to 30x plus 2, right? At 30x, the slope being 30, it's very steep. I can go even steeper by making this 300, and it's so steep that it almost looks like it's a perfect vertical line, but that's an illusion, right? There's no such thing. This thing is just so incredibly steep, it kind of looks like that, but it's not. Right? Vertical lines are not described this way. If it was actually a perfectly vertical line, then we have to use this notation, x equals a constant, like say 4. Now that would be a perfectly vertical line um, where the line is described by just the statement x equals to 4. Good. Remember, the slope is undefined for this purple one. Any questions? Okay, easy stuff, right? Moving on over here. Okay, so if we have a linear equation of the form f of x equals to 2x plus 1, then again, this is a linear equation with a slope of 2, y-intercept of 1. Here we can see a quick little sketch of it. It's got a y-intercept of 0, comma 1. Here's the equation. If I wanted to find other points, I can use the slope. And this is a really good way of practicing this. Right? The slope is 2, m equals to 2. If we want to use that information to find other points and do a rough sketch, we would like to convert this into a fraction. So we can just always put a little 1 underneath. And now we can use this as the rise, and this is the run. So now we can come back over here and do 1 unit this way, the run, and then the rise, and the rise goes up to there. So 2 units that way. And we arrive at another point. So it looks like we go to 1 and up by 2. This is going to be the point 1, comma 3. Good. Questions? This one is a linear equation. That's this y. So f of x equals to 3 is the same thing as y equals to 3. And this one does still stick to the general form of the y equals mx plus b. Right? The only one that doesn't fit that pattern are vertical lines. Horizontal lines do fit the pattern because we can always stretch this to mean 0 times x plus 3. The y-intercept is 0, comma 3. The slope is 0. So this line right here, the slope is 0. Questions? Anyone? No? Easy? Good? Okay. So any function of the form x equals to the power of n are called power functions. And there are different, there's a few patterns that we need to remember with any equation that fits this form. So the power functions are anything that fits this form. So obviously some of the famous ones. Oops, I forgot. The x, f of x equals to x to the n power. So most common ones are f of x equals to x to the first power, of course. Equals to x squared. F of x equals to x cubed. And f of x equals to x to the fourth. And f of x equals to x to the fifth power. That's all you really need to look at, because beyond that, the pattern stays the same. This is going to be a linear equation. In fact, I think, oh, well, that's fine. This is going to be just a linear equation, right? So the y-intercept is going to be 0. So a rough sketch of this thing is just going to be the line that goes through the origin. Oh, that failed. Just to go through the origin. There. Good. This one has slope of 1. slope equal to 1, and y-intercept of 0, 0. Good. Okay, this one is just a quadratic. Hopefully we're familiar with it, with the vertex equal at 0. It's just a nice common standard function. And its graph is going to look like this. We'll use technology in a little bit and get even better pictures. But this is just a standard graph of a parabola centered at the origin. Good. X cubed is going to look very similar to the parabola. Extend it out here. It has this sort of a pattern and comes down this way. So it's kind of like this thing here, but then you just twist this down and curve it down in toward the quadrant 3. And this is supposed to go through the origin, so that looks kind of ugly there. That's this guy. And then for these guys, they follow the same patterns as this. They look very similar. So x to the 4th power looks a lot like this one, except it gets more kind of squared off, where x to the power of 4 goes down and kind of becomes a little more squared off. It goes down toward the x-axis faster from the point 1, 1. So we have 1 there and 1. And then over here we have the point -1. So within this little zone, when we have even powers of 4, 6, 8, this kind of gets squared off a little more and goes toward the x-axis a little bit faster. And then from this point forward, it goes up toward infinity a little bit faster. So it looks more and more like a squared off parabola. The bigger the power, the more it fits that form. And similar for this guy here, at the point 1 and 1. And then over here we have -1 and down to -1. In this little zone within -1 to +1, as we go to powers of 5, 7, 9, these things are going to get a little bit more squared off. They go toward the x-axis faster. And then beyond that, they go up to +infinity or down to -infinity faster. You can use technology to do a better job of graphing those as well. Where did that thing go? So y equals to x is just a straight line. Y equals to x to the power of 2 is a parabola like this. And then as we do different powers, y equals to x to the power of 4 that are all even. See, from the point, from this point and this point, from -1 to +1 along its domain, from within there, you see that the graph gets more squared off. It goes down toward the x-axis faster. And then from that point forward, it goes toward infinity faster. Right? So this one is x squared. The red one is x to the 4th. Let's see, y equals to x to the 5th. I'm sorry, x to the 6th. Gets even more squared off, right? So this is x squared, x to the 4th, x to the 6th, right? And you can see the pattern here. See how it gets more squared off. It goes down toward the x-axis faster. The bigger the power, as long as it's even, it goes down toward the x-axis faster within -1 and +1. And then outside of those things, it goes toward infinity faster. So you get this sort of shape, right? So if I pick x to the power of some really big even power, then this thing will almost look like a vertical line comes down here. It comes down here pretty quickly toward the x-axis, so it'll just look like a glass. Right? Y equals to x to the power of, I don't know, how about 30? See how the green one just looks like a glass? Just it comes down here. It almost looks like a vertical line, but we know better. We know it's not a vertical line. but almost looks like it. It still goes through the point -1, 1 and 1, 1, and then it kind of squares off pretty quickly here, and it almost looks like a flat base here, but it's not. It's just that it approaches 0 so fast that to the naked eye it looks that way, but it's also never really horizontal. It's just a sort of an extreme version of the original black one. Good. Any questions about these? No? Okay, y equals to x to the power of 3 looks very similar to this one. So here is x squared is this black one. So you see that it on the in quadrant 1 they look very, very similar, except x to the power of 3 between 0 and 1 goes toward the x-axis a little bit faster. That's because 3 is bigger than 2, and we just saw that as the power gets bigger it goes toward the x-axis a little bit faster. And then from this point forward, x to the power 3 goes to infinity a little bit faster. So on the right-hand side, it follows the same pattern as before. But on the left-hand side, over here, when the input value is negative, raising a negative number to the power of 3 is still going to give us a negative number. So it just allows negative values and comes down here into quadrant 3. Okay, so let me get rid of this. So this is the iconic graph of x to the power of 3. And then as we go higher in powers that are all odd, x to the power of 5, again we follow the same pattern that between -1 and 1 on its domain, in that region, the new higher power is going to go towards 0 faster, so it kind of squares it off this way and it squares it off that way. And then outside of those regions, the function is going to go toward positive infinity or toward negative infinity faster. So this is the pattern that emerges. Very similar to the previous one. Y equals to x to the power of 7. Oops. The power of 7. You see it's even more squared off. Let's pick another really big one. Y equals to x to the power of 9. Good. So let's zoom in again. So they all go through the point 1, 1. The original one is this purple one. That's x to the power of 3. And then x to the power of 5, and x to the power of 7, and then x to the power of 9. So the bigger the power, the faster it goes toward the x-axis and squares off around here. The bigger the power, the faster it goes toward infinity in this zone over here. Good. They all go through the origin, 0, 0, and then they go down in this direction. And again, they all go through this point, -1, -1. Right? So all of these functions, all of them have the same 3 points in common. It's just the pattern changes a little bit based on the regions. Right? So through here, they're still negative, but they go toward the x-axis faster and faster and faster, depending on the power. And then as we go farther into this direction, the bigger the power, the faster it goes toward negative infinity. Okay, any questions on these patterns? No? 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 Okay. All right, moving on. So let's look at, we looked at x squares, we looked at x cubes. What about the square root function? The square root graph can also be written this way, remember, that h of x equals to the square root of x is the same thing as x to the power of 1/2 or x to the power of 0.5. It just makes it easier to graph that way. So again, let's just use Desmos. Fixing those things. So we have y equals to x to the power of 0.5. So this is the pattern that we get for the square root, 1/2. And then if we look at y equals to the cube root, how would we do the cube root? So that would be y equals to x to the power of, and then the cube root would be 1 divided by 3. So the purple one is the cube root. So they are very similar to looking at the powers of 2 and the powers of 3, just kind of tilted on their side. Good. Questions, questions, questions? And then moving forward, the same pattern happens where if we have, let me rewrite this as 1/2 so it kind of fits the pattern. Power of 1 divided by 2. Okay, so here's the 1/2 one. If we do 1/4, 1/6, 1/8, all the even ones, they will be similar to this green one. Y equals to x to the power of 1 divided by 4. Except this squared off thing happens again, but in a different direction. Good. So the green one is just the square root of 2, and this one is the fourth root of, the square root of x. This one is the fourth root of x, and if I go to the sixth root, it'll just kind of come up here and be a little more squared off. Still goes through this point and then goes below this black line over here. So that's the pattern that happens with all the even roots, and then all the odd roots will follow this pattern, where this is the cube root of x, and then if I use the fifth root of x, the seventh root of x, all of them we know are going to go through this. Come on. Why is it fighting me? Okay, well, it's going to go through the point -1, -1. I don't know why it doesn't want to keep it. Anyway. And then if I use a different power, like the fifth root of x, it's going to get more squared off here. It's going to go this way, go through the point 1, 1, and then go up slowly. This direction, it's going to go this way, a little bit more squared off, and hit 1 there, and then go this way. Y equals to x to the power of 1 divided by 5. We get that. Any questions? Well, now it'll let me label them. Any questions on these patterns? No? 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 Good. Okay, so here's some tables to be able to find these patterns. Oh, graph these functions by creating tables. Okay, so tables. If you didn't have these patterns memorized, if you've never seen them before, how would we know that this was a parabola and this was the graph of a x cubed? Well, we start off by creating tables, creating ordered pairs, and from those ordered pairs, we'd establish the patterns, right? So we can again use technology to speed up the process, but we can get a couple going. So if someone had no idea what this was and how to graph it, why not just start evaluating input values? So 0, 0 squared gives you 0, and then 1, and then 1 squared, that gives you 1, and 2 squared, that gives you 4, right? So you can just keep going that way. -1 and -1 squared, that gives you 1, and -2 and -2 squared, that gives you 4. Right? And so you can just keep going this way, keep going that way, and establish a pattern. So, let's go this way. Okay, so let's go back to this. What we could do is establish a table. Where's tables? Tables. Equals x 2. There we go. Okay, so we can just graph a bunch of results. So if I had no idea what x squared was, I can create a little table like here and just plug in values. So the value of 1 is mapped to 1 because 1 squared is 1. So here's my little dot. How about 0? 0 maps to 0, okay, so then we get this one. Negative 1 squared is 1, so we get this one in there. So we can just keep going and try and find values. 2 maps to 4, and then of course negative 2 also maps to 4, so we get that point over there. And we can keep going. And it doesn't have to be just whole numbers. I can try some decimals. 0.2 squared is 0.04, so that's how we get this value right here. How about 0.5? How about 1.5? How about negative 0.7? How about negative 1.4? So we can just keep going, find more and more values. And as you can see, we're starting to fill in the pattern that we're looking for. And as I do this an infinite number of times, eventually we start to see that all of these form this pattern. Whoa, that pattern. Eventually, all those little dots begin to form this shape, right? So when you see a graph like this one, a parabola, it's useful to sometimes think of it as an infinite collection of dots that form that graph, right? An infinite collection of ordered pairs that establish the relationship between the horizontal variable and the vertical variable. Good. We can do the same thing for x cubed. We can do the same thing for the square root of x. We can create a table, evaluate this equation for different input values, get an output value, graph all of these ordered pairs, and eventually you see that we get the shapes, graphs of those functions. Any questions? So here they are. Good. Questions, comments, issues? Okay, piecewise functions. Easy stuff. So sometimes a function is defined differently for different parts of the domain. So here's an example of what it might look like. Here we have a function f of x, which is described by this relationship whenever the input value is this, whenever x is strictly less than or equal to 1. This is the function that describes it. Whenever x is strictly greater than 1, then this is the equation that defines it. So in order to graph these, you're going to have to graph both of them and then chop it up based on the domain. Break it up based on the domain. Good. So we know that the equation of x squared is just going to be a plain, boring parabola. I know this guy goes this way, and this guy goes that way. So this is x squared. And then 2x plus 1, so this is y equals to 2x plus 1, tells me the slope is 2. And it goes to the point 0, 1 as the y-intercept. So let's graph this guy over here. Okay, so 0, 1, let's say it's there. And then as it goes through slope of 2, I don't know, maybe it goes like that. Something like that. Good. Okay, so now what happens at 1? So at 1, this gives you the point 1, 1. At 1, this gives you the point 1, 3. So at 1, we have 1, 1. Looks like I have let's make it an open circle. That one is 1, 3. And then at 1, we had the point 1, 1 over here. Well, let's say that's 1, 1 for the parabola. Okay, so according to these instructions, if the input variable x is less than or equal to 1, we follow these instructions, right? So we're going to have for x less than or equal to 1, less than or equal to 1, we're going to follow the parabola. So that's going to be this thing over here, going over here in green. And for for x being greater than or equal to 1, we're going to follow these instructions. So it's going to be this open circle there, and then we're going to go this way. And looking at this, we need a closed circle there, and then an open circle there. Okay, so we would, at this point, erase everything else, and our graph would just be the green part. It's that part there made up with this part over here. Any questions? No? No? So you have to graph them both. You have to think about the domain and break up your graphs based on the domains. And think about where they equal each other, or what happens at the points where the domains intersect or something. I'm not sure why that's there. Anyway, here, this is what it would look like. We follow the instructions on the parabola up until we get to this value. It's a closed circle. And then we jump over and follow the instructions of the straight line. Right? This would be a straight line that continues this way, but we're only going to have this little ray starting from this point, which was the point 1, 3. Any questions? No? 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 Pretty easy? Okay, the greatest integer function. It's quite a useful little function that's described with these little almost like brackets with an extra line through them. The greatest integer function always equals the biggest integer that is definitely less than or equal to x. So it brings it down to the value, the first integer to the left of that number on the number line. That's how you can think of it. So here's some examples. If you plug in a 2 into here, the output is just 2, right? Greatest integer that's less than or equal to it. If we put in a 2.3, the answer is 2. If we put in a 1.9999, the answer is 1. Okay, so it's not rounding, right? So this often gets confused with rounding. But we're not rounding, otherwise this would just round to 2. Okay, so it's the biggest integer that's smaller than this. You can think of this as money, right? We have whole number, like bills and coins, some kind. So you're just counting how many bills you have and kind of ignoring the coins. Questions? Any questions? Any questions at all? Do we have a mic issue? Somebody have their mic on? Or is there a question and I can't hear? Okay, anyway. So these values just round down to the greatest integer. And then it gets a little trickier with the negative ones. This gets a little complicated. But remember that it's always the first integer to the left of this number on the number line. Right? That's what it means to go to the greatest integer that's less than or equal to that value. So negative 3.5 on the number line. Right, so here is 0, here's 1, here's 2. So if, let's put negative 1, negative 2, negative 3, negative 4. So if we're looking at input values of 2.3, so here's 2.3 right over here, then when we apply it into the greatest integer function, this is going to give us a 2. It's the first whole integer to the left of that decimal value. right? The biggest integer that's smaller than this one. If we put in a 1.99999, it's going to be like right there, 1.999999 into the greatest integer function. The answer is going to be 1, right? It's the biggest integer to the left of it. So if we're over here at negative 3.5, we always go to the first integer to the left, and so the answer is negative 4. Any questions? No? No? And then negative 1.5, negative 0.5, we apply it to the greatest integer function, is going to be negative 1. Questions, questions, questions? No? Okay, here's an example that uses it. A global data plan costs $25 a month for the first 100 megabytes and $20 for each additional 100 megabytes or a portion thereof. Okay, so draw a graph of costs of C in dollars as a graph of the number of megabytes X used per month. Okay, so let C of X be the cost of using X megabytes of data in a month. So X is always going to be greater than or equal to 0, right? So you can't use negative megabytes in a month. You have to use 0 or higher. So its domain is values from 0 to infinity. Good. Okay, so now we can kind of create a table to organize our results, and it's going to be based on the amount of data that we use, right? So we want to break up the domain. When we use between 0 and 100 megabytes inclusive, right? The first 100 megabytes, we just pay $25. Beyond that, if we use 101, 130, 199, if we use any number of megabytes that lands in this section of the domain, then this becomes our new bill. It's going to be the original 25 plus $20 for a $45 bill. If we use between 200 to 300 megabytes, then our new bill will be 65. Right? 2 times 20 plus 25, the original $25 fee. Good. Okay, so now how do we describe this? How do we graph this? This is often called a stepwise function for obvious reasons, right? It looks like a bunch of little steps. But notice that these right here, this graph describes exactly this pattern right here, which describes this situation. So remember, there was a $25 fee for using anywhere between 0 to 100 megabytes. So that's what this is saying. If X is any value between 0 and 100, the bill is going to be 25. On the other hand, if we use even one tiny megabyte beyond 100, and notice there's a dark circle here, so at exactly 100 we're still at 25, but anything beyond that, even a tiny little bit beyond that, our bill just jumps up to here. It's not a smooth transition from here to here, it just jumps to the next level, and I believe that that's going to be 45. Right, so again, we lose precision when we use graphs, because if I just presented this to someone, it might be hard for them to figure out what does this mean, what value is that exactly, but we do gain some perspective in that we get to see sort of a global pattern that happens. So there's some benefits to graphs, of course, some drawbacks as well. Good. Any questions about stepwise functions? No? No? We're good? Okay, the vertical line test, super easy. So the vertical line test. A vertical line test is a little test we can very easily apply to a graph to be able to determine if that graph is the graph of a function, if it qualifies as a function. So a curve is in the coordinate plane is the graph of a function if and only if no vertical line intersects the curve more than once. That's all we do. I'm sure we've all used it before. So here's some examples. If we have this blue graph, What we want to do is visually inspect it. Think about this line sweeping back and forth, and we're going to be keeping track of how often or where does it cross our curvature. Right? So if it only touches it at one point at a time, no matter where as you slide it, it only touches it at one point at a time, then the curvature is the curve of a function. On the other hand, if the curvature does something like this thing here, and then as you sweep this line back and forth, you notice that it touches at more than one place at the same time, for example here, then we can say that it fails the vertical line test and that this curvature is not the graph of a function. Good? Looks familiar? Yes, yes, yes. Why is that? Well, remember that in order for a relationship between an input and an output variable to qualify as a function, it must be true that each input gives you one unique output. Right? We saw that yesterday. That's the definition of a function. So when we're looking at these curvature here, right, this blue curvature, it's useful to think of it as an infinite number of dots, where each dot represents a relationship between an input, right? When I input the number, I don't know, 3, maybe it outputs the number 7, right? So there's that relationship, and it's described by this ordered pair right in there, right? I just made up these numbers just to establish that relationship. And remember that for it to be a function, it must be true that every single input must go to an output. It's okay if more than one input leads to the same output, because notice that if we go over here, here's another number, I don't know, maybe 8. 8 leads to 7, but so does 3 leads to 7. That's okay. And in fact, maybe this one also leads to 7. Maybe that's the number 3.5. 3.5 leads to 7, 3 leads to 7, 8 leads to 7. That's okay. These are all fine. What we cannot have is a case where the same value goes to two different outputs. So let's say, for example, here we have 3, and then according to this graph, it leads to 7. Okay, 3 leads to 7, but also 3, going up here, 3 also leads to 9. Right? So 3 leads to 7, but 3 also leads to 9. That's not a function, right? Not allowed. Can't have that. No, that's too messy. You can't have a case where the input value goes to two different outputs. Any questions? No? This should be really easy. There's no mathematical equation, right? It's just a concept we have to keep in mind. So if you're thinking about your homework, how is this going to be applied? Well, they'll just give you a bunch of equations, a bunch of graphs like this, and you just have to look at them and determine which ones would qualify to be the graph of a function, right? So for part A, right, as we sweep this back and forth, we can clearly see that it's going to touch the curvature at more than one spot in lots of places. And so therefore, this is not the graph of a function, right? It's some sort of oval or circle or something. So it's not the graph of a function. As we sweep a vertical line in this function, we see that it's only ever going to touch one point at a time. So B is the graph of a function. C, same thing. As we sweep a line through there, we see that it only touches one point at a time. So as we kind of think about these vertical lines, okay, it touches there. If I do a vertical line as it sweeps, it only touches there. There's no vertical line where it fails. So this is the graph of a function. And then clearly it fails for this last one, so not a function. Any questions? No? 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 So just to clarify, this is not a function. This is a function. This is a function. This is not a function. Questions, 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 questions? Okay, which equations represent functions? Okay, sometimes that can get a little confusing. If an expression is given to you and you're asked to determine whether it's the equation of a function, a useful thing to do is to first of all spend some time using our awesome algebra skills to convert it in solve for y. And once you've solved for y, hopefully it's a little easier to determine if it's the equation of a function. And remember, the guiding rule again is that every time we input one value, the output is uniquely determined. One of the ways that we will often see this fail is if the y has an even power, like say 2 plus x minus 3 equals 4x. Let's say we have something like this. As I try and solve for y, I know that, okay, I'll move this over there, move that over there. I'll end up with y squared equals to 3x plus 3. And now I'm going to have to take the square root of both sides. And when I take the square root of both sides, I know I'll end up with a plus or minus square root of 3x plus 3. Right? This plus or minus out in front tells me that there's going to be two different answers. When I input an x value, there'll be two different outputs. So I can already tell that this is not going to be a function. Good. So solve for y, and hopefully it'll be clear there whether or not you'll be able to preserve the principle of a function. Good. So not every function works. Okay, so let's look at this example. As I solve for y, I can tell that I'm going to be able to get the equation of a function. This is just going to be x squared plus 2. Every input gets squared plus 2. That defines a unique value. So this is going to be a function. Right? In fact, it's a parabola, something squared plus 1. So what happens when I take a parabola and always add 2 to every output? It's going to shift the whole thing up. Good. Let's look at that. So here is a parabola of y equals to x squared. And if we always add 2, let's look at a table value where we always add 2. What the hell? Okay, so plus 2. And let's change this to let's make it a red. Okay, so the black one is x squared, and then these little red dots are going to be x squared plus 2. So x squared should have taken me to 1 when we input a value of 1. 1 squared is 1. But then if we add 2, that automatically moves you up to 3. 0. 0 should have taken you to 0. 0 gives you a 0 when we square it. But then because we're adding a 2, that gets us to 0, 2. Good. How about negative 1? Negative 1. Negative 1 now maps to 3. And then we can throw in some decimals to figure out what happens in the middle there. Good. So you can see that it's starting to create that sort of curvature thing, same as this. If I zoom out a little bit more, let's try some larger numbers. How about 2? How about 3? About negative 3, about negative 2.6, how about 2.7? Okay, so what we start to see is that this guy here starts to become equivalent to this one, but shifted up by 2. So the whole thing can be graphed like this: y equals to x to the power of 2 plus 2. So eventually all those little dots start to form the same parabola, but the plus 2 shifts it up. Good. Okay, so that's what this is going to be. And clearly this does form the graph of a function. It's a parabola. And inspecting it on inspection of the equation, every input gets squared plus 2. Every input gets a unique output. On the other hand, we've worked with these before. This is the equation of a circle, right? It fits the general form of a circle, x minus h squared plus y minus k squared equals to r squared. Here, the h and the k equal 0. So we have a circle centered at the point 0, 0, right? That's what these tell us. And the radius is going to be 2, right? 2 squared is 4. So it's just a standard circle centered in the origin. And knowing that it's a circle, I already know that it's going to fail the vertical line test because as I sweep lines through this, vertical lines through it, I can see that there's going to be an infinite number of places where the line touches at 2 points. In fact, there's only 2 points where the graph only touches at 1 point, where the vertical line only touches at 1 point. So that would be this point there. That's supposed to be a straight line. And this point here, right? The points where the lines are tangent. At this point and at this point, the vertical lines only touch at 1 point. But at every other place, the lines touch at more than 1 point. Good. So this is not a function. Upon inspection, we can also tell that as I solve this, I'm going to end up with something of y squared format. I'll end up with y squared equals to 4 minus x squared. And then as I solve for y, I'm going to end up having to do the square root of 4 minus x squared. Again, I get a plus and a minus. There's going to be 2 solutions. One input is going to result in 2 outputs. Therefore, I know that this is not a function. Any questions? No? No. Okay, same thing. We solve for y. We see that every input has a unique output. Solve for y. We see that we end up having to do the plus or minus. One input is going to end up with 2 different outputs, the positive end and the negative end. Good. We can graph them, do the vertical line test, and again we see that it touches at only one spot at a time as we sweep this left and right, and here it touches at more than one spot. Good. The Desmos allow us to see the vertical line testing a little bit better as well. Let's change this to be black. Let's get rid of this thing. Let's get rid of that guy. Okay, so here is the line, the curvature y equals to x squared plus 2. And let's do the line y equals to, I don't know, b, where b is this slider. Where we go? Let's make it red. And b is right here. Okay, so here is the vertical line sweeping through the function, and we see that as it sweeps through it, it only touches the graph at 1 point at a time. Let's do how do I get it to be equal to that? Equals to comma b to the second power plus 2. Do it that way. Okay, and then we can label it. There we go. Okay, so now as I sweep through, you see that that point, it only touches at 1 point at a time. Good. Questions, questions, questions? And then we do the same thing here. And as I sweep through it, we see that it would touch at more than 1 point at a time. Any questions? No? No? Okay, so some classic functions, right? We have linear equations that fit this format. Power functions, we covered this a little bit already. Powers of n, the general pattern that happens. Here is x squared, and then all the even-powered ones, like this one, and to the 6th power and to the 8th power are going to look like this, just more and more squared off. And all the ones that have an odd power, like x to the 3rd, x to the 5th, and so on, have these general patterns. And there's a couple of other common ones. So we briefly looked at roots as well. So all the even roots are going to have this general pattern, and all the odd roots are going to have this general pattern. Good. And then reciprocal functions, we didn't look at these today, but hopefully they look familiar. Again, these are the general patterns. Again, the ones that have an even power have a very similar shape. So 1 over x, 1 over x, 1 over x cubed, 1 over x to the 5th. All the odd ones are going to have a similar pattern, and then all the even ones are going to have a similar pattern, right? Mainly that the output is never negative when we have an even power. And then the graph of an absolute value equation looks like this, like a V shape. Hopefully that looks familiar. And then the greatest integer function, which we covered today. So hopefully these graphs are mostly familiar. I think maybe greatest integer function is new to most people, but hopefully the other ones are familiar. And you know, if you're not sure, if you're not quite sure why it has that sort of shape, like maybe you haven't seen the absolute value function before, then Desmos is a great way to convince yourself that that's the graph of an absolute value. So if you come over here and graph it, come on, go away. We can go back to the table format and graph a bunch of ordered pairs. So x1, okay. And then we want to do absolute value. Where's the absolute value? Where'd it go? Okay, I have to go over here. Functions, stats, just the miscellaneous. Okay, oh, absolute value. Here it is. X1. Okay, so here's a little table of values. 1 leads to 1, 0 leads to 0, -1 leads to 1, 0.5 leads to 0.5, -0.4 leads to positive 0.4. So all these ordered pairs, like this one and this one and this one, right, these are the ordered pairs that are described when we create this table for absolute values. And you see that eventually, as we fill in this blank even more, let's say maybe we type in a -2.8 or type in a positive 1.9, right? As we create more and more of these dots, eventually they begin to fill in the shape of a y equals of x. They begin to fill out that shape, right? So it looks like a V. That's why the graph of the absolute value function absolute value function looks like this V shape. Okay, moving on to section 2.3, another super easy section, getting information from graphs. So we're going to look at values of functions, looking at the domain and range. We've done that a little bit, so we're just kind of expanding on that. We're going to compare function values, solving equations and inequalities graphically. We've done a little bit of that as well. Increasing and decreasing functions, local max, local min, also fairly easy stuff. So should be an easy section. So many properties of functions are more easily obtained from a graph than from the rule that describes the function. We will see in this section how the graphs tells us whether the values of the functions are increasing, decreasing, and maximums and minimums of the functions. So first of all, domains and ranges. as we've seen before, the domain is all the possible input values. The range is all the resulting output values. Right? A complete graph of a function contains all the information about the function because the graph tells us which input values coordinate to which output values. Okay, so we want to analyze the input and output values. Here's an example. Let the function t graphed in figure 1 gives the temperature between noon and 6 p.m. So here is between noon and 6 p.m. So x, the input value, is the time. So here t equals to 0, x equals to 0 represents noon. So here, this value right there would represent noon. And then this is 6 p.m. And then we have our temperature, right? So temperature in Fahrenheit, it starts off, looks like 15 at noon and gets warmer and warmer and warmer. And looks like we hit the highest temperature of looks like about 35 or 34 around 2 p.m. And then temperature begins to come back down, and we get back down close to 15 by the time 6 o'clock rolls around. Okay, so we have a nice little picture to describe the temperature. So let's find some values, some information from this graph. So for example, let's find t of 1, t of 3, and t of 5. So this notation, this is function style notation, right? So this is letting us know that I want the temperature when the input value is 1. So this is x equals to 1, when x equals to 3, and when x equals to 5. So all we have to do is read 1, 3, and 5 from here. So when the input is 1, this traces up to this point right there. So it looks like the answer is going to be about 25. When it is 3, looks like it goes all the way up to there. So that looks like it's going to go up to about 30. And then at 5, it looks like it goes up to there, which is again about 20. Good. So it looks like we have the ordered pair 5, 20. At 5 o'clock, it should be about 20 degrees. At 3 o'clock, we get the ordered pair 3, 30, approximately. So it should be about 30 degrees at 3 o'clock. And at 1 o'clock, we get the ordered pair 1, 25-ish. So we get those results. 25, 30, 20. 25, 30, 20. Good. Very easy, right? Okay, which is larger, t of 2 or t of 4? So here's all of these guys. T of 2, okay, so here is 2. T of 2 reaches to there. Now remember, it's not exactly up to that level, so it's not exactly 35. It's a little less than that. In fact, let's make it a different color since I don't want to mix it with the other ones. I don't know. Let's make it blue. So t of 2 is here, and t of 4 is here. Right? So we wanted to compare t of 2 and t of 4. Right? Those were the instructions. T of 2, T of 4. Okay, so people often confuse this. The input value is 2. For this one, the input value is 4. So of course, 4 is bigger than 2. But T of 2 represents the output. It represents this. So this height right here is T of 2, whatever it is. T of 2 is somewhere around there. Whereas T of 4 looks like it's exactly this. So maybe T of 4 is somewhere around there, around 25. So here we could see that T of 2 is higher than T of 4. Right? So T of 2 is greater than T of 4. Good. Any questions about that? T of 2 is bigger than T of 4. Follows that T of 2 is larger than T of 4. Yep, that's what we wanted. Okay, next question. Find the values of x for which t of that value equals to 25. Equals to 25. So we kind of want to reverse engineer this and find the values that work. Let's erase this stuff over here. Okay, so 25 is here. The output is 25. And we want to find all the values of x such that f of t equals 25. So if we kind of go back, we see that there's 1 point there, and then we kind of go backwards and see that the answer would be 1. If we let x equal to 1, we should get an output of 25. And then again, going backwards this way, we run into the other one. And it looks like the other answer is x equals to 4. So in solving this statement, oops, right, x equals to 1 and x equals to 4 are the two potential solutions to this. Any questions? Pretty easy, right? Let's see, C is that what they did there? 1 and 4. So the temperature at 1 o'clock is about 25. The temperature at 4 o'clock is about 25. Man, can you imagine living in a place where the warmest part of the day is 34 degrees? Not fun. Anyway, find the values of x for which t of x is greater than or equal to 25. Very similar to this previous question, except here we want to find all the values where t of x is equal to or greater than 25. And so that's going to be this section of the t-axis. Come on. Starting from here, I want to figure out all the input values that result in a value higher than 25. I want f of t to be greater than, so greater than or equal to, yeah, greater than or equal to 25. So I want to find all of these values, right? So it describes this part of the curvature like that. Right? All of these output values are bigger than 25, and then if I trace that down to the shadow, we see that all of these values, let's put a different color on there, how about orange? We see that all of these values between here, all of these inputs, including 1 all the way up to 4, all of these values are the values such that the result, the output temperature, is above 25. Any questions? Right, so all the values between 1 and 4 result in a function that is equal to or higher than 25. So between 1 and 4, the temperature will be above 25. And then the last one, find the net change in temperature from 1 to 3 p.m. 1 to 3 p.m., the net change in temperature. Let's erase some of this stuff. Okay, so let's find them between 1 and... Oh, go away. Net change in temperature between 1 and 3 p.m. So between 1 and 3 p.m. Come on, there it is. Okay, so here is 1, and then that changes to there, and then 1 and 3 p.m. So this changes from there to there. So if we think of this little triangle that can be formed underneath this curvature, and maybe orange isn't the best color, we can look at this little triangle here, and we could see that this represents the change in the output temperature, whereas this represents the change in the time, So the distance from here to here is the change in the x, but the net change in the temperature is described by this, which is the f of, the t of 1 value, which is this value there, and then this one, which is the t of 3 value, which is, looks like it's about there. So we can see from the graph there's a net change of about 10 degrees, right? This goes from about 20 degrees up to 30 degrees. So the net change is going to be 10 degrees. Net change is 10 degrees Fahrenheit. Did I make a mistake?
When you're done.
Oh, yeah, no, go ahead.
Is it always kind of going to be like an estimate, or will it always, I mean, like in the ballpark roughly?
So graphs, yes, we lose precision when it comes to graphs. I can't tell exactly where it is down to a decimal, so we just kind of guesstimate it. Now, when we're given an equation, then we can be very precise about our answer. But if a graph is given, we kind of guesstimate it, and someone might look at this and go, no, that's not really 30. That's that's 31, or that's 30.5. Something like that. Well, it's a good enough guess. So these questions are not about getting a precise answer. If someone told me the net change was 9 or 11, I would go, okay, either one of those are pretty good answers. But someone tells me the net change is 75, like, oh yeah, that's not right. So lots of good answers, that are close to the right answer, but there's definitely a point where it doesn't make any sense anymore.
Okay.
Good? Okay. Let's see. And then what did they put on here? Oh, wait a minute. See, look at this. What did I do wrong here? 25 and 20 for 1. See, look at that. I read this wrong. Well, this was just way off. This is definitely a good point. T of 1 is not 20. I don't know where I got 20 from. 20 is way down here. T of 1 is this. This is 25. My net change is 5. It's not 10. Right? So this guy traces over here and gives me a 25. And that's T of 1. T of 1 goes to 25. So the net change here is not 10. I made a mistake. It's 5. Is that why you were asking? Because you were noticing that there was something really off?
Yeah. I was also going to ask, like, what if they were asking, like, what's the change in, like, 1 to 230? I mean, like, is it ever going to be, like, something like that?
Oh, again, so 1 to 230. If the question was 1 to 230, again, you cannot get a precise answer. You go, okay, where's 230? Okay, about halfway, somewhere around there. And you kind of trace it up. And then you go, okay, it's around there somewhere. Okay, and what is that equal to? Okay, well, that's 30, that's 40. This must be 35.
Yeah, like somewhere around 32. But I was just
about 32. Great guess. So maybe this is 2.5 comma 32. And we don't know the precise answer. If you're just giving a graph like this, we lose the ability to be really exact. However, we gain a lot. We gain perspective on seeing the overall pattern, and that could be very valuable. Sometimes you want a very precise answer, and sometimes you just want a good guesstimation, right? Just to kind of overall see where the pattern is heading. Is it getting bigger? Is it getting smaller? Right? So not only do we see the general value at 230, that it's going to be around 32 degrees, but we can also see what's happening throughout the day, that we have this little hump that goes up to around 2 o'clock and then comes back down. So we see a general pattern. We see that it's decreasing starting at around 2 o'clock. The temperature begins to just go down, 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 down. And so we get some information from that. Good. But yeah, don't worry about being super precise at this point. Good. Any other questions? No? Good. Don't overthink this. This is an easy section. Shouldn't be too scary. So in general, whenever we're given a curvature, some sort of graph described here in the red, this is the graph. then as we kind of see, think of this as the shadow. If we see the shadow of this curvature along the ground here, around the x-axis, that describes the domain. So this is all possible inputs of this defined curvature here. So that would be the domain. And then this one gets a little more confusing for people. It's all possible outputs. So if we kind of slam it across this way, or the shadow across the y-axis, right? If we have a giant light source over here going this way, we see the range values. That often gets confused with this. Let me put some numbers on here, if this will let me. Man, this thing is not happy right now. Come on. So I just to put some numbers on here, let's say that this is the number 1, 2, and this is the number I don't know, 7, 8. So the domain is going to go from 1 to 7, right? So the domain can be described as 1, 7 with brackets. And the range, so this is where people get confused. So here is the range 2, and they think it's from 2 to 8. But that's not it, because the 8 is this number right here. But that's not the highest possible value. 8 only maps to like around there, right? I want this point. This is the one that's going to tell me the maximum value on the range. So if this was labeled as, say, I don't know, 6, 10, then the range would go all the way up to 10, right? So this would be the range. The range would be 2, 10, inclusive. Right? Whereas this is the domain. So my point was just that it's not just about the last point and the first point and the last point. That's not always the way to find the domain and the range. You have to be careful to make sure that you are inclusive of all possible inputs, all possible outputs. Again, if you're just given a graph, a picture, then you just have to look at the picture and judge from the picture what the domain and range are. And again, you can't be super precise when just the picture is given. But when we have an equation, it gets a little bit more complicated then, because we have to take our equation and figure it out from there, figure out what the domain is and figure out what the range is. And particularly the range can get a little confusing, a little difficult to find. Good? Thank you. Good. Okay, for example, use a graphing calculator to draw this graph. And then find the domain and find the range of this graph. Okay, so let's first of all use Desmos, and then I'll look at our graphing calculator. So going to Desmos, 4 minus x squared. Let's get rid of some of these things we don't need anymore. Man, I use a lot of things. Okay. F of x equals 2. F of x equals 2. Let's see if we have a root here. Giant root of 4 minus x squared, was it? 4 minus x squared. Okay, so it says to graph it, so this is that's what we're supposed to do, find technology and graph it. And Desmos does a great job, so here it is, that's what it looks like. And so from the graph, we can tell what the domain and range are going to be. So the domain is going to be all possible inputs, so that's going to be all values trapped between -2 and +2. Right? Any one of these values can be plugged into this equation to give us a possible answer. Now, why aren't any of these values in there? Think about what happens when we try and plug in x equals to 3. If we plug in an x equals to 3, we're going to get 4 minus 9. That's -5. The square root of -5 is an imaginary number. So there is no real number solution when x equals to 3. Good? So the only real number solutions come when the x value is between -2 and 2 inclusive. What are the possible output values? Well, it's always positive because we only have the positive root here. So the output values can only be positive answers. And then the smallest value it could be is 0, because if we let x equal to 2, then we get 4 minus 4, which is 0. Square root of 0 is 0. So the smallest value this could be is 0. And what's the biggest value this could be? Well, we're always subtracting a positive number, so the biggest value inside the radical occurs when x squared is as small as it can be, and the smallest it could possibly be is 0. So 4 minus 0 squared is going to be 4, and the square root of 4 is 2. So the largest possible value that this can take on is a 2. So from the graph, remember this is at this point we're just trying to solve this by graphing. So we graph it, we see the picture, so from the picture I can tell the domain is between -2 and 2, and the range is going to be from 0 up to 2. Good? Questions, 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 questions? No, no, no? Okay, let's practice using our, well, okay, let me close this guy, leave. Let me write it down. So we found that the domain was this goes this way, this goes this way. This is kind of like the top half of a circle, right? And this goes from -2 to +2 to +2, and so the domain is going to be all of these values over here. That's the domain. And then the range is going to be all the possible output values that we get, which is going to be all of these values here. So the range is going to go from 0 through +2 inclusive, and the domain is going to go from -2 to +2 inclusive. Good. Okay, so this is the graphing section. It's important to learn how to use your graphing calculator. Hopefully you guys all have one or borrowed one from the school. That form is still available. I'm pretty sure they still have calculators available at school if you need to borrow one. So let's look at how to graph this on a calculator. And the short answer, okay, so let's see if it'll work, because I have a lot of programs working and the computer is not happy. So let's see. Finder, launch. 84. No, continue the trial version. One other option for you is that Texas Instruments, the manufacturer of TI-84 calculators, because of the whole pandemic, is offering to let you install this TI-84 emulator for free. Just type in Google Texas Instruments or TI-84 free trial, and they should give you like a 3-month free subscription to this. So you get to download this program. It's a simple little program on your computer, and then it just mimics exactly what a TI-84 calculator looks like. So it's good to learn from it here. It'll be great as long as this whole study from home situation happens. But at some point, you'll go back into the classroom setting, and in some classes, you'll be allowed to use a graphing calculator, and it'll be good for you to be aware of it and be able to to use it when you need it. So it's a good place to learn. But for now, if you don't have access to a physical one, then this is a good option to download the emulator. Make sure you go directly to the company TI-84. I mean, Texas Instruments. Here, let's do it, right? Because otherwise, you don't want to accidentally download a virus or something. TI-84 emulator, free. Type that in. and you're looking for ti.com, Texas Instruments, so education, whatever, free trial service thing. So I'm pretty sure they're doing it for students as well, that you can download a 90-day free trial thing. They did it for me, but I think it's also students. Anyway, try it out, let me know. Anyway, how do we graph it? Okay, so this is the screen that normally sits right above your calculator. Right? That's what this is. It just made it a little larger. So what we want to do, whenever you get your calculator, the first thing you want to do is go over to where it says mode and check the status of your calculator. So it's in normal mode, it's in float. If we type in an angle, it's going to be in radians. It's in function setting, that's what we want right now. Later we'll look at parametric polar functions. Dots are thick, sequential, real numbers, full. Okay, everything looks pretty good here. If something is not like this on your own calculator, you can use your arrows here, go left and right, down, up and left, right. And if you want to select something, then you hit enter. So if I wanted to change it to degrees, for example, I can select degrees, hit enter, and then now it's in degree mode. Good. Put it back in radians, enter, we're good. Okay, so now when you want to get out, hit quit. So the little quit button is right above where it says mode, but it's written down. So we have to hit second and then mode, and that qualifies as the quit. Right? In this is really old technology from like the 80s maybe, these calculators. So a button can do different things based on the writing. So there's like the actual button has writing on it, but there's a little writing above in different colors. So if you want that other value, you have to hit the second or the alpha buttons first to give you that result. So if I wanted to type in 7, for example, I could just hit 7. But if I wanted the green O, then I hit green, and then I hit O. And, well, that looks like a 0. So let's do P. If I wanted P, I would have to hit the green first, and then the 8, and then that writes down the P. Good. If I want V, then I would hit the second, and then that gives me a V, and I type that in. Okay, so keep that in mind. All right, so to graph that equation, we're going to go to y equals. That gives you this kind of a thing. And we want to type in a giant root. Now, a giant root on your calculator is pretty ugly to do. But, okay, so it's right here, a giant square root. So we're going to hit second and then root. That puts the whole thing in a giant square root. And it was 4 minus x to the second power. So there's an easy button for x squared, which is this one, and this is the value of x, right? The variable x is going to be right here, and then we want to have that squared, so 4 minus x squared. Good. Hopefully that works. Now, an alternative way of doing it is to use those power symbols, the little caret symbols. So instead of doing the square root of, I can say that this is equal to, let's put it in parentheses, open parentheses, then 4 minus x squared, close parentheses, and then to the power of, that's what this little caret symbol does, to the power of. Now the newer calculators do this kind of thing where they bring you up to the little exponent. If you have an older calculator, you see the little caret symbol appear. And you have to know that that means that you're in the exponent. So now we can raise it to the power of 1/2. Good, so this is the same as that. Good? Questions, questions, questions? No? No? Okay, so next we're going to go over to our window. Well, okay, so let me erase this. I don't want them both. Just pick one of them. So to graph that, okay, so now I'm going to go over to my window, and I got to choose a good window. Let's pick, I already know by default, I kind of already know what I'm graphing. I'm going to graph this. If you don't know what you're graphing, then the window of -10 to 10 is good enough, and then just kind of play around with it, or -20 to 20, right? So what we're choosing is the x minimum. So the x minimum is going to be this value over here. How far to the left do you want your window to be looking? And x max is going to be over here, the maximum value. And then y min, y max, same thing. Minimum y value, maximum y value. We'll play around with those for change them to see what would happen if we change those. When you're done typing in the values you want there, you hit graph, and you'll see it there. So because I put negative 10, positive 10 for the x min, x max, and y min, y max, that means that this is negative 10 here, and way over here is positive 10 for the x min, x max, y min, y max. As you can see, it's a bit of an overkill. The picture is way in the center here. So what we could do is go back to our window and bring this in a little bit. How about if I make this negative 3 to positive 3, and I can make this, I don't know, how about negative 4 to positive 4. Graph. And so you see I have a slightly better picture now. So this goes out to negative 3 and positive 3, x min, x max, y min, y max. In fact, I could tell I don't even really need anything down here. The actual graph does not go into quadrants 3 and 4. So if I wanted to, I can go back to my window and set my y minimum down to 0. And then the graph would look like this. Oh, even better. Looks a little more like that one. Good. So you can just kind of play around with the window settings to make sure you catch your whole image. Be careful though, because if you do something like, let's make this go from negative 10 to positive, let's say it's a negative 5. If I choose a window like that and I graph it, I'm not going to see anything. My picture's not there because I focused my window so far to the left. It's in just a small little section of quadrant 2 that my picture is not in the image. Right? It's somewhere over here. So be careful to choose a good window for your graph. Like I said, by default, if you don't really know what you're doing, you might want to pick a standard setting like negative 20 to positive 20 and see if that kind of gives you an idea of where the graph is. Right? And of course, keeping in mind that these calculators are really old, the screen doesn't really have that many pixels, so you get kind of a warped sense of the picture often. So keep that in mind. Okay, any questions so far? No? Okay, so let's go back to a good... Oh yeah, go ahead.
Yeah, Desmos does everything. Right?
Oh yeah, and more. Desmos is awesome. If I knew that you had Desmos available always, I wouldn't even bother with this calculator anymore. The only reason... Oh yeah, go ahead.
No, I was just saying, once I learned Desmos from you, it's like, oh, well, it's a lot nicer.
Yeah, way nicer. Yeah, so much nicer. The only reason we bother with the TI 84, the only reason this company still exists really is because physical calculators are only allowed, in certain classes and certain standardized exams. That's the only calculator that's allowed.
It's like the standard, basically.
Exactly, right. But I'm sure that, sometime soon that's probably going to change. We're getting to a point where it's reasonable to expect that everyone just has a laptop. So in a classroom setting, instead of saying, hey, everybody pull out your calculator, very soon people say, just pull out your laptop, we're going to work with this program, and you'll see that this thing is going to die soon.
Yeah, okay.
But for the moment, it's good to learn. And you get used to it, and it is pretty nice to just have something that is pretty robust and reliable and direct. The laptop, you have to open it, you have to password, and then you have to open the program. Sometimes the program has to connect to the internet.
You could put on your phone, do you know, or no?
I have no idea. I've never really looked. They might have an app, so that could be good too. Okay, so back to this guy. Okay, so we got the domain, we got the range, we could graph it, we feel pretty good about it. Here's another nice little image of the whole thing. So we have the range, we have the domain, and we get all that from its graph. Good. Okay, comparing function values, solving equations with inequalities graphically. Okay, we can compare the values of two functions f and g visually by drawing their graphs. That's another great way to use graphs. You can figure out when they equal each other, which is where they cross, where they intersect. And then from those, we can easily tell when one graph is larger than the other from the graphs of the two functions. Good. So, for example, if we have a g function and we have an f function, we can easily tell from the graph when they cross there and they cross there. That means at x equals to a, both f of a and f of g, g of a and f of g, and f of a equal each other. Write that down. Saying that at this point right here, this is a point where f of a equals g of a. Come on. At that point right there. Right? And at this point right here, this is a point where the output of f, which is at b, f of b, equals to g of b. Right? So we can easily tell when both of these equations are going to be equal to each other right when they cross. And we can also tell the sections of the domain where the g function is larger than the f function, or where the f function is larger than the g function. Good. So we can tell that in this little segment of the domain, the g of x function is going to be larger than the f of x function. So this part right here is true. So if we were trying to solve this, find x such that f of x is less than g of x, we know that if we graph it, we can visually tell when that's true and find the domain that solves that. Good. Questions, 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 questions? Okay, so for example, solve the given equation or inequality graphically. Okay, so don't solve it algebraically, solve it graphically. So we have 2 of x plus 3 equals 5x plus 6. Okay, so the first thing we want to do is define the left-hand side of this equation by some function f of x, and define this side of the equation by some function 5x plus 6. Next, what we want to do is graph them both and figure out where they cross. So again, we can use technology. Let's use Desmos again. Desmos. Graphing calculator. Okay, so we're going to define f of x to be the left-hand side, which is equal to 2x to the second power plus 3. Right, that's this part here. And then we're going to define g of x to be the right-hand side, g of x to be equal to 5x plus 6. Okay, so here is the graph. And from the graph, we can easily tell where they cross each other. So here's one intersection point, there's another intersection point. So Desmos makes it extra easy. You just have to get kind of close to it and click, and it'll show you where they intersect. With the calculator, it gets a little trickier. We'll cover that in a second. But we can easily tell that these are the 2 points where they will equal each other. So when when the input equals to negative 0.5, both functions will have the same output of 3.5. And when x equals to 3, both functions have the same output of 21. So those are the 2 solutions to this equation. Does that make sense? Questions, 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 questions? So now that I have the really nice graph over there, then I can do like a really, whoa, not that ugly, like a really rough sketch of what this thing looks like. And do I have a, well, okay, never mind then. So from the Desmos, I could tell that this was the general graph. And we could tell that these ordered pairs right there were 3, 21. And the other one was this one, negative half and 3.5. Negative 1/2, comma 3.5, 3.5. Good. So we can tell that those are the two answers to part A. F of x and g of x are equal to each other whenever x equals to negative 0.5. Negative 0.5 is x there. And x equals to 3 is the other answer. Any questions to this one? No? We'll cover how to find that intersection in a calculator real quick in a second. Okay, next, when is the 2x squared plus 3 less than 5x plus 6? Okay, so we said the way I defined it, this one is f of x. When is f of x, which is the parabola looking thing, less than g of x? That's what we're looking for. When is f of x less than or equal to g of x? And again, from our picture, when is the parabola smaller than the line? So we could tell that that's this little zone right in here. Let's change colors to say green. Okay, so I can tell that in this zone, in between these, for this domain right here, in this little section right in here, oops, then in this little section in green, it's true that the f of x function is less than the g of x function. Good? Any questions? Questions? So for part B, the answer is going to be this set between negative 0.5 and positive 3, inclusive of the endpoints because it wanted that. And then, of course, the opposite, when is the f of x function greater than the g of x function? Well, that would be for domain values over here on the left-hand side or over here on the right-hand side. Okay, so for part C, we get the opposite. For any one of these values, the f of x function, right? So like if this thing is a value of x, so if we choose x to be, I don't know, what is this? 1, 2, 3, negative 3.5, for example, then this would lead to some value there of the f and some value here for the g, and then the f would be larger than the g. Good. So this and this, which is described this way, is the sections of the domain for which the f of x is greater than the g of x. Any questions? Sort of, kind of, maybe. Okay, so let's cover how to use our calculator to do that. Okay, not as easy. So we want to type in 2x squared plus 3, and then 5x plus 5 on your emulator. So let's go back over here. So we want to go back to y equals. Let's get rid of that one, the old equation. And we're going to type in 2. X is this button here. The power of caret squared, so that's 2x squared. Make sure you put the arrow to get away from the exponent, and then plus 3. So that's one equation. And then the other equation was 5x plus 6. There's the other equation. Let's pick a good window. By default, let's just try negative 10 to 10. Nice square window and assess it from there. Negative 10 to 10. And see what it looks like. Graph that. So there's the parabola, there's the line, and I can see, oh, look at that, it's out of the window. So I'm going to go back and readjust my window. I don't need to go all the way to negative 10. Looks like negative 1, 2, 3. Looks like -3 captures everything I need on this side. And then on this side, it looks like, well, it's kind of hard to tell exactly where it's going to be, but maybe around this far. It's really the positive y maximum value that I want to increase. So let's go to this. -3 we said was good enough for the x. Let's go to a y maximum value of, say, 40. See how that covers it. There we go. That looks better. Okay, so I need to figure out when these two things cross, where they intersect, using our calculator. On Desmos, you just click it and it just gives it to you, but we don't have that clicking ability on our calculators. So we're going to use this button that says trace on here. Above it, it says calculate. That's what we want to do. Trace is the easier way of solving this question, and some teachers might be okay with that, but it's also very imprecise. So it's just a couple extra buttons and then you get a more specific answer. Use this little button that says calculate. So hit second and then calculate. And what we want to do is this, the intersection. So go down, use your arrows, hit enter, and then follow the instructions. First curve, question mark. Okay, so look, here's the first equation. It was a parabola in blue, and then if you hit up, then here's the second equation, and it's this one. And you can just keep going up and down, right? Up and down, and it'll just go back and forth between them. There's only two, so it seems like kind of a silly question. But keep in mind that I might have a case where there are a lot of graphs. One graph is a parabola, another graph is a circle, another graph is a line, somehow a absolute value in there. There could be lots of graphs in there. So when you ask the calculator where do they cross, it wants to know which curvatures. So all you have to do is hit enter, and then it asks you for the second curvature. It automatically jumps anyway to the other one, so you can hit enter again. So when you only have two equations that you're dealing with, you just have to hit enter twice. It's really when you have 3 or more functions that you have to care about making sure that you're choosing the correct ones. Okay, next, the third question now is for you to guess. And so you just use your arrows to go left and right. See how I can go left and right, travel on the curvature. Right now I'm traveling on the straight line because I have this equation there. So I'm traveling left and right on it. On the other hand, if I go up by 1, uh-oh, didn't let me do that. I thought it did. Never mind. I thought it let you jump to the other equation. For some reason, it doesn't seem to want to do that. Anyway, it's asking you to guess. So travel along that curvature until you get to the one that you want to approximate. Notice that there are obviously two answers. So if I just hit this right now, the calculator won't know which intersection you want. So you just have to get fairly close to it. You don't have to be super precise. It's somewhere around there. Just close enough so that the calculator knows that you want this intersection as opposed to this intersection. Okay, so hit enter. It'll calculate it and then give you the exact answer, 3, 21. So all that work was to mimic what Desmos does right here when you click this, and then just gives you 3, 21. Okay, to find the other one, to find this one over here, you have to repeat the whole process again. So now if I want to figure out when does it cross over here, we're going to have to hit second, calculate, the fifth option down. So you can either use your arrows down, hit 5, enter, or you can just hit the number 5, and then follow the instructions. Remember, when there's only two curves, you just have to hit enter twice. Pick the first curve, pick the second curve, and then get to the part where it says guess. And now we want to get away from that guess and come over here and try and guess this one. Hit enter, and now it gives you the other solution, -0.5, 3.5. Any questions about that process? No? Good? Good? Okay, so once you graph them, once you find the intersections, then you are able to solve these types of questions. When are two functions equal to each other? When is one function greater than another function? And that could be really useful. Okay, moving on to increasing and decreasing functions. Spotting when a function is increasing and decreasing is very easy from a graph. And initially, that's all we're going to do. So a function is going to be given, like this one, and you just have to identify the segments of the domain for when the function is increasing, and the sections of the domain for when the function is decreasing, and so on and so forth. Doing it from a picture just involves looking at it and judging it, and hopefully that's really, really easy. What we're doing is we're building toward being able to do the same thing when we're given an equation, right? So you can picture this as an ugly polynomial equation, right? X to the 5th power minus 4x cubed plus 7x, something like that. And then looking at just the equation, how can we tell when the function is increasing, when it's decreasing, right? So some of the key characteristics of it. Well, if you're just given an equation, one thing you could do is, of course, use technology to graph it and then judge it from there. But if you don't have the technology, how can we do it? Well, that gets complicated, right? That's what we're building toward doing. But for now, all we have to do is look at the graphs. So this section is still very easy. And I think it's pretty intuitive of when the function is increasing. Here it is. It's going up. You can picture a little person walking on it from left to right, the way we read. And if that little stick person, here's my little stick person. Wow, it's a terrible stick person. There. If that little stick person is going up from left to right, the way we read, if it's going up, it's increasing, kind of like slope, same as slope. And then if that little person is going downhill, from left to right, the way we read, if he's going downhill, then that's decreasing. Good? Questions, 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 questions. Okay, so from a picture, we can easily tell when he's going up, he's increasing, decreasing, right? And so we can tell the sections of the domain where the function is increasing. F of x is increasing between a and b, right? So this is for x between a and b. The function is increasing. For x between b and c, the function is decreasing. And for x between c and d, the function is increasing, right? So we can easily tell from the picture. Again, we're just building toward being able to do it with equations down the road. And then a more precise mathematical description of what it means to increase and decrease is this guy. Don't let this scare you too much. It's just kind of building on our understanding of mathematical expressions, but it's really a very simple explanation that, again, you can just kind of visually see it, right? This is increasing, and this is decreasing, right? Again, a little stick person walking from left to right would be going uphill here, and a little person walking from left to right, the way we read, from left to right, or most of us, will be going downhill. So this is decreasing. So symbolically, what we can say is that this function is increasing if it's true that f of 1 is less than f of x of 1 is less than f of x of 2 whenever x of 1 is less than x of 2, right? Which is exactly what we see here. Whenever it's true that this one is smaller than this one, right? The smaller one, if we evaluate it, leads to an f of x sub 1 that goes right around there. Let me erase that stick person, he's in my way. Okay, so f of x sub 1 leads there, and then f of x sub 2 leads there. Pretend those are straight lines. X sub 2. And you see how f of x sub 2 is the larger value. F of x sub 2 is larger than f of x sub 1 whenever it's true that f of x sub 2 is larger than f of x sub 1. When the bigger value in the domain leads to the bigger value in the range, then we have a case where it's increasing. And then the opposite is true. when the bigger value in the domain leads to a smaller value in the range, right? So here is what f of x sub 2 leads to, and here is f of x sub 1, f of x sub 1. So in this case, the f of x sub 2, this one leads to, it's bigger than this one. F of x sub 2 is bigger than f of x sub 1, but the output, let me say that again, x sub 2 is bigger than x sub 1, but the outputs are the other way around. The f of x sub 2 is smaller than that one. So whenever that's true, we have a case where the function is decreasing, right? F of x sub 1 is bigger than f of x sub 2 whenever x sub 1 is less than x sub 2, right, on that interval. Okay, so don't worry too much about this definition right now. This is not difficult. This is not a difficult section. We're just trying to find a math way of describing increasing and decreasing for graphs, but you could just look at them and be able to judge when that is. Good. And then just spend some time looking at this. I think eventually it'll click in. Questions, 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 questions. Good. If we wanted to sketch a more complicated graph like this one using technology again, we can type in this polynomial, and then from the polynomial we can find from the graph of the polynomial we can find the domain and the range. The domain is going to be really easy, right? Because it's a polynomial. The domain of all polynomials is all real numbers. There is never any value I can input into this polynomial that would result in either a undefined, that would result in undefined from either dividing by 0 or taking the even root of a negative number. The more complicated thing is to figure out the range. What is the maximum output of this? What's the minimum value of this thing? And so it'll be easier to find the range by graphing it. So find the intersection on which f is, or find the intervals on which f is increasing, on which f is decreasing. Okay, so let's do it with Desmos first, and then we'll extend that to our calculator. So this is going to be 12x to the power of 2 plus 4x to the power of 3 minus 3x. And let's get rid of this guy. Oh no, 3x to the 4th power. Okay, so I typed in the correct answer, 12x squared plus 4x to the 3rd power minus 3x to the 4th power. Okay, so this is what the graph looks like. And it keeps going on that way forever. So I know the domain is all real numbers. But the range, I could tell that the biggest value this could ever be is described by that value right there. Right? So the range is everything below that. Everything below 32 is the range, where the domain is all real numbers. It might look better if I zoom in. Any questions about that? Right, so now I can do a rough little sketch here. This guy. And I know that this is going to have, let's make it this way. It did like a little thing and came up here, whoa, and then came up there, and then came back down here. Ugly little sketch, but if we find some of the key values, it's good enough to be able to describe what this graph looks like, right? So if they wanted a really nice sketch of this, it would be nice if I found this point, that point, that point, that point up there, that point down there, and then indicated that it went down toward negative infinity from there. They didn't ask for an incredibly detailed graph, so I think this is good enough for now. We just have to find a few of these key points. And again, Desmos does a fantastic job of all of that. So I can identify this point and that point and this point and that point and that point. and find all the key features I want of this graph using technology. If I didn't have technology, then this would be a whole lot of work, and that's what we're building toward. Finding all the places where it crosses the x-axis. Those are all the x-intercept points. Okay, there's 3 of them, and we'd have to find those individually. Finding out where this little hump happens. We're about to talk about that. A local maximum, the global maximum, figuring out where that happens. That's also a lot of work algebraically. But luckily we have technology right now. So 232, negative 1, 5. So this goes 232 and then negative 1, comma 5 for this one. Okay, so the domain and range. The domain is going to be all real numbers. From negative infinity to positive infinity. And the range is going to be all numbers starting from negative infinity all the way up to the maximum value that it could be, which is at 32. So it starts at negative infinity and up through 32, inclusive of 32. Right, 32 is a potential value. Good. Any questions? I want to label this as the y and x-axis. Right, looks like that. Good, 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 good. Okay, how do we find that in our calculator? How do we type that into our calculator? Let's do that real quick. So let's clear this, go back to y equals, let's clear that equation, go back there, clear that equation, go up here. Okay, so we need to type in this really ugly equation. So I like to wrap it in parentheses because some of the older calculators have really ugly user interfaces here. So raising all those powers can get kind of ugly. So 12x to the power of 2, close parentheses. Oops, see how that got ugly? Delete that. Close parentheses. Plus, open parentheses, 4x to the power of 3. Screw over, close parentheses, minus, parentheses, 3x to the power of 4, close parentheses. Okay, so there is my equation, and then the window, right? So if I didn't know where this was going, okay, by default, I like to do negative 20 to 20. And then reassess from there, depending on what the graph looks like at that point. Just the standard window of negative 20 to 20 graph. And I can see that I get most of my picture, but I'm missing part of it, so I know I'm going to have to let my y maximum go higher. I also can tell that I don't need to go all the way out to negative 20 and positive 20. It looks like very small values along the x-axis are good. And same thing for y. So the only one that needs to be big is the y maximum. Going back to my window, let's change this from negative 4 to positive 4. And negative, I don't know, 2 to positive 50 graph. Okay, so now it looks a little better. Looks like that. Okay, now I want to find this thing, right? From my graph, I could tell, you know what, I'm uncomfortable with this being so little, so let's just change my y minimum to be a little bit bigger. How about negative 10? Good, okay, so now from my picture, I can tell that this is what I'm interested in, just this guy up here, for the purposes of finding the range, right? I can tell that I don't necessarily need that one for the range. It might be useful for other reasons, but not for the purpose of finding the range. That's the maximum value there. So how do we find that maximum value? So we're going to use this calculate button again. Second, calculate. And you see how it says maximum? We want to go down to where it says maximum. Maximum, hit enter. And now follow the instructions. It says left bound, and then it's going to say right bound. So you want to travel with your arrows here along the curvature, and you want to stay close to where you want to find the maximum value, somewhat close. but to the left of it. So say there, I'm going to hit enter, and it creates that little left bound. And now you want to go over the hump to the other side, somewhere on the other side, say over there, and then do the right bound. Hit enter. So what you've done is you've created or you've identified a little section of the domain in that little zone. And so now you hit guess. So go back to pretty close to where you think the max is. Hit enter, and now it finds the exact answer, 2,32. Good. So from that, we're able to come up with our rough sketch and be able to tell that this is 2,32. That this is 2,32 as an ordered pair. And now I can tell that every value from here below will be the range. As this travels over here, and you get to 32. Then everywhere down here, going down toward negative infinity, all of these values will represent the range. Any questions? No? Good. Okay, local maximums and minimums. So again, from the graph, it's really easy to identify what the maximum point, what the minimum points are. So we will be working with graphs and being able to spot them from the graphs. Later on, we'll build into cases where we have an equation and we have to find it from the equation. And these are really useful because there's a lot of places, a lot of applications where we want to find the maximum or we want to find the minimum. If we can come up with an equation that models a real-world situation, such as interest rates or production costs or just any number of real-world situations where an equation describes it. I don't know, speed of air around the wing of an airplane, the weight of a rocket as it's shooting up into outer space. It's obviously starts off really heavy because of the fuel, and as it's burning through the fuel, it becomes lighter and lighter and lighter. So there's some equations that can describe that. So we want maximum, maximum thrust as a function of the weight of the rocket, stuff like that. So we want the maximum, the minimums, all the time. So again, if we just have a nice pretty picture, a nice graph, we can easily tell what all the local maximums are, right? It's a little hump, right? It's the king of the hill in a little section of the domain where the function is the maximum value. A little section of the domain where that little value there is the minimum value, right? That's what local maximums are. As you can see, you can have several of them, several local maximums, several local minimums. And then we'll define something called a global maximum, where global just means over the entire graph, which one is the absolute biggest one. Whereas this is just the biggest one in a little section of the domain. Good? So the function value f of a is called a local max of f if it's true that f of x is greater than, f of a is greater than f of x when x is near a, right? So looking at this picture here, what we're pointing out is that this, come on, cooperate with me. We're almost done. Thank you. Okay, so we're saying that we'd say that this value there, x equals to a, we would say that x equals to a, well then that maps out to f of a. F of a is called a local maximum if it's true that there exists a little neighborhood around the value a, a little subsegment of the domain here, such that whenever you pick any x value in this little neighborhood, any other x value in here, and you evaluate it, in that little section, right, this leads to this. Here's f of x. For any other x value in this little green zone, not including the a, of course, it's always true that f of a is bigger than f of x. right? That's what this is saying. F of A is greater than or equal to f of x whenever x is near A. And that's what defines a local maximum. And then similarly, a local minimum. So let's say that this guy over here, I'm just going to use a different letter. Oh, that's fine, we'll use A. So let's say that this guy is the A over here. This is A. We would say that this maps to some value over here, which is f of A, and it is considered a local minimum because if we think about a tiny little neighborhood around A, then whenever we pick any value of x in that little neighborhood, whenever x is chosen to a value close to there, it's always true that f of x is bigger than f of A. Therefore, we consider f of A to be a local minimum of that value. Any questions about these definitions? Good. Okay, so again, don't let these definitions scare you too much right now. At this point, we're really just focusing on finding answers from a graph. So I think that that's pretty intuitive to find. And we'll also be using calculators a lot, or technology, Desmos, to find them. So graph them, and you can easily spot where the local maximums and minimums are. Good? Okay, so again, graphically, we take our equation, we graph it, and we can see that that point right there would be a local maximum at f of A, and that this point right here would be a local minimum at f of B. Good. Questions, comments, issues? Notice that f of A is greater for all x close to A. Similarly, if there's a viewing rectangle. Okay, so that's just a matter of putting it on our calculator. So find this, round it to 3 decimal places. Okay, well, I think that this is the same skill that we just did a little bit ago. So we just covered how to find maximums a minute ago. It's the same thing for minimums. So I think you can take care of this. Yeah. Okay, that brings us to the end of this section. Any questions? I just didn't do... Oh, yeah, go ahead.
Yeah, this is more of a question for the homework.
Yes.
Could you post the homework? It seems like people in the group chat are wondering if... when is the homework for... Because you only posted till 1.7, and I think people are wondering, should they do the homework up to 1.7, or...
Yes, I have to go through and find the other exercises for the rest of Chapter 1. Okay. So I'll try and get to that today. So I think there's about 4 more sections in Chapter 1 that we covered. So I'll post those homeworks up. Chapter 2 is already up, so you should be able to get started with some of this stuff here in Chapter 2. You know, because I had to cancel class on Monday, I'm gonna have class tomorrow. So same time tomorrow, 8 a.m. If you are able to join, fantastic. If not, then it'll get recorded and then posted on YouTube, so you can catch it on your free time. And wherever we stop tomorrow, which is going to be pretty close to finishing Chapter 2. Like as you see, this section is pretty easy. We go pretty quickly through material. So wherever we end tomorrow will be the cutoff for our test next week, and on which we're shooting for Tuesday. On Tuesday, you'll submit your homework for all of it, and we'll have our test. Did I answer all the questions?
Wait. When is the test again?
Tuesday.
Okay, Tuesday, and then one more. Can you post the PowerPoint with your notes on it?
Oh, yes, I'll do that.
Thank you very much.
Any other questions from anyone? We're good? Okay, have a great day, and hopefully I'll see you tomorrow.